So we are in jumping up an entire chapter to 7.4. So I just had a weird thought when I wrote Surfaces of Revolution. I thought of Che Guevara, and I thought of revolution in that context. This is a weird mixture. All right. So what I want to do first is we want to come up with a formula for how we're going to find the arc length of a particular curve. So I'm going to draw a little piece of a curve. So here are 2 points. Here's some curve, and we're going to use I as our index. We're dividing our curve into little pieces. So if I draw this is a magnified view. If I draw the curve over here, we're dividing it up into little pieces, and I have just one of these pieces over here. So this point is going to be x sub I and f of x sub I. And we'll go backwards here. So this is going to be x I minus 1 and f of x sub I minus 1. So there are my 2 points, and we have our function here is y equals f of x. And I'll call this point p sub I and p sub I minus 1. So our arc length, we can approximate the arc length by taking the sum of these small segments. So I'm going to draw this segment here, and we're dividing our curve into these tiny little pieces. So we can approximate the arc length of the curve by adding up all the lengths of those straight little segments. And then what we want to do is make our interval between x sub I and x sub I minus 1 smaller and smaller and smaller. So the length of this little segment I'm going to use a distance formula. D sub I is square root of x sub I minus x sub I minus 1 squared, just using the distance formula, plus, I already have the plus there, f sub x sub I minus f x sub I minus 1. We're going to square that quantity. And the arc length we're going to call S. Is going to be the sum, I equals 1 to n, for however many intervals we divide that up into, of d sub I. I'm going to add up all those little segments. This argument of subdividing things, little pieces, and then adding the pieces together, taking the limit, we'll see that a lot over the course of the year. It's it's one of the foundational ideas of calculus, but we're going to develop a lot of things by going back to this argument. By the time we get to the end of second semester, we'll just say we're going to use our familiar argument of dividing things into intervals and skip a lot of the in-between steps. All right, so now we're going to go way back in time to kind of close to the beginning of Calculus 1. And we're going to say on the interval, x sub I minus 1, x sub I, we're assuming that we're working with a nice continuous a continuous function, so our curve is smooth. So on this interval, the mean value theorem. Guarantees us that, what happens? We can remember what the mean value theorem tells us on an interval in a situation like this. Perfect. So the mean value theorem guarantees us that the slope of this segment is equal to the derivative of the function at some point in that interval. So at some point in the interval, there's going to be we'll be able to find the derivative where the derivative and the slope of this segment are the same. That was a perfect statement of what the mean value theorem is. Nice job. All right. So it says the mean value theorem guarantees us that there is a w sub I, some point in the interval, such that f prime at this point equals the slope. Because what we're trying to do is somehow manipulate this into something that we can actually use. So I'm going to rearrange this, and I'm going to say that I'm just going to multiply by the denominator here. So I get that f xi minus f xi minus 1 equals f prime at some point times this change in the x value, xi minus 1. So let's call this xi minus 1 delta x sub I. That's just our change in our x value at that particular place. So I can rewrite this distance formula with this quantity instead of these f sub x's and f sub xi's minus 1. So I'm going to plug this into my distance formula. So I'm going to switch the pages. Is everybody good with what we've done so far? So we use the mean value theorem. We're finding an expression for this. We want to turn this into something that we can actually work with. So we're going to say, so our little increment of distance, d sub I, equals the square root of delta x sub I squared plus f prime at w sub I times delta x sub I, and that whole quantity is squared. I'm going to factor out these delta x sub I squareds and then take the square root. So d sub I equals the square root of 1 plus f prime at w sub I, some point in that interval, and this is squared. times delta x sub I. And our arc length is the sum, again, of these d sub i's over this interval. And we're going to let delta x sub I approach 0. So we're making our little interval smaller and smaller and smaller. We get a better and better approximation. So motivated by this idea that we can use this to approximate our arc length, and we're going to take the limit as delta x sub I approaches 0. We're going to define our arc length using this quantity. And I think I mentioned it before. I had a professor when I was in college that said, when you make it your definition, no one can touch you. So you motivate your definition, and then we say, this is my definition. This is how I'm defining the arc length. And as long as your motivation makes sense, then your definition's fine. So we're going to say define the arc length, motivated by this development. So we call our arc length S of f, some function on a nice interval, a to b. S equals the integral from a to b of the square root of 1 plus f prime of x squared dx. And we're assuming that f is continuous and smooth on our interval. So our function isn't doing anything strange on it. So this is our definition of the arc length. We motivated it with some geometric arguments, used the mean value theorem, but this is our definition. And something you've all seen before. So what do you remember about arc length integrals? So the first thing that I think is I see this radical, and I see this at 1 plus f prime squared. It looks like they're going to be messy. So a lot of times arc length integrals are very messy. Depending on your function, 1 plus f prime squared can be kind of messy. You might not be able to take the square root in an easy way. So arc length integrals a lot of times are kind of ugly integrals. But they do lead to some nice techniques of integration in order to solve it. So any questions on our development here? Okay, I just want to do one quick example with an arc length integral with a new kind of function that we just learned the other day, and then we're going to talk quickly about surfaces of revolution. Okay. So we have a cable between two towers. And they're 200 feet apart. When cables that are not ideal, so not cables that don't have any mass that we talk about in physics, but cables with mass, when they hang between two supports, they take the shape of a catenary. And the catenary is given by a hyperbolic function. So in this case, let's see, and the towers are, what do I want to say, the towers are 200 feet apart, and at the midpoint, the cable is at 150 feet. So the shape in this case is y equals 150 hyperbolic cosine of x over 150. And if I drew a quick picture here, here are my towers. Here's my cable hanging between these towers. We're going to put our y-axis right here in the middle. Put this end at positive 100, this end at negative 100, and then here in the middle y equals 150. So that's a quick sketch of what we're talking about. We want the length of the cable between the towers. So we're talking about the arc length of this curve. So let's calculate the quantities we need for our arc length. So we need f prime, or we need y prime here. Oh, not y prime. So y prime, what is y prime? Remember the derivative of cosh? Sinh. And then I have the x over 150, so these 150s go away. So I just end up with sinh of x over 150. And this turns out nice. This one works out nicely. Y prime squared, which we need for our arc length, is sinh squared of x over 150. And we need 1 plus y prime squared in our radical for our arc length. So we get 1 plus sinh squared of x over 150, which, thank goodness, equals what? What is it? Cosh squared. So cosh squared of x over 150. So this one works out nicely. We have a nice integral that we're evaluating. So S, our arc length S equals the integral from negative 100 to 100 of the square root of cosh squared of x over 150 dx. And thank goodness this simplifies, because otherwise it could be really ugly. So this just gives me the integral of cosh x over 150 dx. And the integral of cosh of x over 150 is what? 150, yes, 150 sinh x. Sinh of x over 150. And we're evaluating this on negative 100 to 100. Now, how do we evaluate this? How do we come up with a number? Fundamental theorem of calculus. So, but how if I plug in, how am I going to find sinh of 100 over 150? We can use the definition. We can go back to the exponential definition, or if we're lucky, our calculator does hyperbolic functions. So now I can go back to the exponential definition of sinh of x and plug those numbers in. So if I go back to my definition, I get that the arc length equals 150, and I'm going to write this, let me move over so I have enough room. So I'm going to go back to the exponential definition of sinh x. So I get e to the 100 over 150 minus e to the minus 100 over 150 divided by 2 minus 150 and at my other limit e to the minus 100 over 150 minus e to the minus 100 over 150 divided by 2. And I can plug that into my calculator now, and I get that this is approximately 215 feet. Now the book, your book on page 469 goes through the same arc length calculation without using the hyperbolic functions. They go straight from the exponential definition of cosh x and manipulate all the quantities that way. So you might want to take a look at that. I found it much easier to use the hyperbolic functions and then go to the exponential definitions. But they go through the other way. Questions on that problem? My recommendation when you're doing arc length problems, try to simplify the integrand as much as you can before you try to integrate. Because a lot of times there's manipulation that you can do that simplifies your work by a whole bunch. Oh yes, this should be a positive. Yes, thank you. Because I have a negative and a negative. Oops. So questions on that? Okay. So the handout that I gave you goes through. It talks about for surface areas of revolution, surface area of revolution. The main part that I wanted you to see on that handout was just the part about the frustums and coming up with the formula for the surface area of frustum. Because that's what we're using. That's what we're using to define the surface area of revolution. We're dividing our curve into little pieces. We have little straight pieces, and we're revolving that about an axis, and we're saying that is approximately a little piece of a cone. And this side of the cone is the arc length of the curve, approximately, between those two pieces. So that's the connection between arc length and surface area of revolution. Is we're saying we're taking this little piece of the curve and we're revolving it about an axis, so we end up with approximately a tiny little thin frustum of a cone. And that's where the formulas come from. So again, we're going to define the surface area of revolution, and then we use a capital S. As, and we're going to say that the surface area is 2 pi, the integral from a to b of r of x is 1 plus, here's our arc length f prime of x squared dx. And r of x is our radius of revolution. So r of x is the radius of revolution. And then of course if we have x expressed as a function of y, then everything turns into y. We have our r of y and f prime of y, and that would, but our r in here is always our radius of revolution. And the way I think of r is our distance between the graph and the axis of revolution. So however you're looking at it, r is your distance between your graph and your radius of revolution. And again, we're assuming that y is continuous and has continuous derivatives on our interval a to b. All right, so all I want to do with this is just go through a quick example together, and then we'll be done with arc length and surface area. Again, be aware that integrals, arc length and surface area integrals, can be messy. I suggest simplifying, doing some algebraic work on your integrands before you try to integrate. And also be aware that if you just try to numerically integrate, if you use your calculator, depending on the form that you put in for your function, your calculator may not actually give you a good answer, just because of the way the calculator goes through and calculates those numeric integrals. It may not give you a good answer. So sometimes, depending on how you simplify your integrand before you put it in your calculator, changes what your calculator tells you. All right. So again, the idea here is we're taking our little piece of surface area, revolving it around an axis, and we get a tiny, skinny little frustum of a cone. All right, so let's look at a quick example, and then we'll be done. So we want to find the area. So we have the surface, we're generating the surface. Y equals 2 square root x about the x-axis. From x equals 4 to x equals 8. So when I do these, I like to make a quick sketch, just so I know what I'm looking at. So as long as I know what the function looks like or have a rough idea. So what is square root of x is going to be something like this, 2 square root of x, roughly. And then we're going from x equals 4 to x equals 8. So I'm revolving this little piece of the curve around the x-axis. So what is going to be our radius of revolution? What gives us our radius? We're not sure, let's draw it in. Our radius goes from, here's our axis of revolution, is the x-axis. So this is going to be r of x. So what's our what's going to be an expression for our radius of revolution? 2 square root of x, it's just our function. So that's our radius. We need y prime and y prime squared. So y prime for our arc length piece of the integrand. Y prime here is going to be what? What is it? 1 over the square root of x, and I'm going to write that as x to the minus 1/2. And y prime squared is just going to be what? X to the minus 1 or 1 over x. I don't know why I wrote it one way, this way, that way. All right, so now we're ready to substitute into our integral, our arc length, s equals 2 pi, the integral from 4 to 8, our radius of revolution, 2 square root x, square root of 1 plus 1 over x squared dx. This doesn't look very nice. But this lets us do some nice algebra. I'm going to write this as a 4 pi times the square root of x and I don't want the squared here. I already squared it. So what can I do here? What's that? I had already squared it here, so I didn't need to square it again. So this is just 1 plus 1 over x. So this is y prime squared. What can I do here? This gives a nice little trick. Let's add these fractions. So I'm going to find a common denominator, add those fractions. This gives me x plus 1 over x. I want to make sure that dx. And I have a square root of x here, and I have a 1 over the square root of x there. So what happens to those? They cancel, so I get 4 pi, integral from 4 to 8 of square root of x plus 1 dx. That looks better. This is an easy one to evaluate, so I get 4 pi times 2/3 x plus 1 to the 3/2, and we're evaluating on 4 to 8. And I get 8 pi over 3, 7 to the 3/2 minus 5 to the 3/2. When I plug and chug in there. So these little algebra tricks that you can do with your integrand are going to be important when you're working with arc length and surface area of revolution integrals. So something that looks like it could be impossible turns out to be a nice, easy integral. All right, homework. There you go.